here. What I didn't do is I didn't move.
Hello.
Hi. So, yeah, I heard the German. Chinese. It says Chinese. Oh, that's German. Interesting. So, if you're not presenting, maybe you can mute your line because we can hear a crying baby right now. Okay, so it is 101. I don't hear any crying babies anymore, and hopefully I have moved both presenters to the screen where they can advance slides. So AJ, are you still having trouble hearing us and are being connected? I don't know. Somehow we could hear them, but they could not hear us. But our first presenter is Hesham. Hopefully we'll figure out how that's, or the AJ stuff. And I do want to ask us all a few questions as we get started. Just, you know, I appreciate everybody being here. I do want to ask, well, how many webinars you've been to today. I just have a few questions as we get started. And then we'll let Hesham speak in a few minutes. So I've got 3 votes. So we do have 10 other people on the line. So if you guys can try to vote, and I guess I've gotten 4 here. So thank you. These are my regular webinar attendee people, I guess. I can go ahead and end that, and then I do want to ask you whether you know at least one of today's speakers. So yeah, that seems to be the case for most of us. Oh, yep. So several folks up there thinking here. All right, so I'm going to go ahead and go to the next one. Do you work at a Mass UTC university? And I'm guessing most of you guys are going to say yes to this one. Get that one a little bit bigger. No, not quite everybody. So this is good. We definitely want to make this available, information available to everyone. So I do have somebody who says they can't hear. Hopefully they're hearing, to do the audio, you can either have the system call you or you can use your computer speakers. I'm excited about this other, so we don't know if that's a family member or somebody who doesn't work in these other things. So I'm going to go ahead and close that one right now and ask our final question to begin with. Whether you work with connected vehicles right now. Let me make sure I'm broadcasting the results. Yes. So, yeah, so many of you guys are working on connected vehicle projects. Okay, and I guess I'm hearing from the Delaware folks that they're still in. So I'm hoping Hesham is able to hear. He typed in just now that he had trouble.
I'm online with you.
Yeah, I know Hesham's on, but there's somebody named Hesham, sorry. And I will mingle his last name if I say it has typed in that he couldn't hear. So I'm hoping his problems have been resolved. So, all right, so I think we do have everybody. So I appreciate everybody's answers on these questions. I think this is kind of fun that we're not all, hugely knowledgeable about connected vehicles. Some people are doing some things and they're familiar. A couple of others are here to learn. So I'm very happy to get those results as we go. So thank you for joining us, and I do hope that we all will learn something. So just before I hand it over to Hesham, I wanted to remind us of the other webinars in our series. And so today we have our 2 presentations. Hesham is going to talk to us from Virginia Tech. Is going to talk to us about network-wide impacts of eco-routes and route choice behavior and other kinds of environmental ITS applications. And then I think it's going to be Yongqiang Wang, or goes by John, at Delaware, along with his professor, Ajay Prasad, is going to be talking to us about connected vehicle technologies for energy-efficient urban transportation and their project and what they're doing with fuel cell buses in Delaware, which is I'm pretty excited about. So, in October, we're going to have these on the 4th Wednesday of each month. And so in April, we're going to have another Delaware project, which is actually a stormwater bioretention cell project, and then a Virginia Tech project, which is led by Virginia Tech, where they are talking about a bicycle and pedestrian count program to estimate performance measures in Blacksburg. So I'm excited about that. In May, we're going to have a LiDAR for air quality measurement project, which is a group of electrical engineers at Old Dominion, largely working on that. And then we're going to have a UVA and Virginia Tech project in June on the impact of climate change and sea level rise on stormwater design and reoccurring flooding problems. So if you are registered for any of these webinars, we are trying to send you all the reminders for all of the others. So you just need to sign up for one. But if you do register, you should be able to get the announcements and reminders about the different webinars that are coming up. So with that, I'm going to stop this and try to get to Hesham's presentation. But I am excited about doing these 2 connected vehicle presentations today, and we're going to start with Hesham Rakha from Virginia Tech. So with that, with Hesham, I'm going to let you start.
Okay, thank you, Emily, for the introduction. So this project basically is looking at intelligent transportation system applications and intelligent vehicle applications and how they can be used to reduce vehicle fuel consumption or energy consumption levels and emissions. This is a collaborative effort between Virginia Tech, Old Dominion University, Majid Seton is the faculty there, and University of Virginia, Bryant Park. Today, I'm just going to be presenting the Virginia Tech portion, given that we only have half an hour. But hopefully, if Emily will allow us, maybe another time we can give another seminar where we present the full results of the 3 universities.
Yep, we can do that.
Okay. Okay, so in terms of the outline of the presentation, first I'm just going to be going over the eco-routing. I'll be presenting some field results, which were not done part of the MATS UTC, but will lead into the issues that we observed and that resulted in the research that we're doing as part of the MATS UTC. Then we're going to get into the eco cruise control, cooperative cruise control, adaptive cruise control systems, both on freeways and on arterials. So I guess there was a poll. Emily, did you want to ask the poll now, or?
Whenever you want. I just lost it again. So
okay,
I'll find it.
Okay, that's fine. I'll continue, and then whenever you want, just tell me, and you can do the poll. Okay, so.
Okay, actually, I have it now. Sorry. So do you want to try to ask people now?
Okay, sure.
Yeah, I'm trying to make it come out. Come on. Why am I so? why I have it on broadcast. Wow, so you have an intelligent audience there, Hesham. We didn't trick them with our questions.
Good.
All right, so with that, I guess we can end the poll.
Okay, so the first thing we're going to be talking about is route choice behavior and how route choice behavior can affect your fuel consumption and your energy consumption. So in an earlier study that we did here, it was actually Kyung-Oh An. Basically, he lived up in the Reston area, which is at the top here. I'm not sure if you can see my mouse on the screen, but basically, and Falls Church is where the Virginia Tech campus was. And at that time, the fuel cost was above $3 per gallon. And the question he wanted to answer was, which route should he take to get from home to work in order to minimize his fuel consumption? He had two possible routes, one which was a more direct one, which is the blue one, but it was along an arterial where there were a lot of signalized intersections, versus a longer distance route, which is the red one, which involved travel on some highways. However, the red route, although it was longer in terms of distance, it was shorter in terms of travel time. And the question we were trying to answer was, which of those two routes was the better route to use if we were considering fuel consumption as our sole objective function? So in terms of the characteristics of these routes, basically the travel time on the highway route was around 25.5 minutes. The travel time on the arterial route was about 30 minutes, so it was about 4 to 5 minutes longer to take the arterial route. And basically the standard deviation of the travel time was a bit larger on the arterial route compared to the highway route. However, if you look at the distance traveled on each of the routes, the distance on the highway route was around 22 miles. It was only 17 miles on the arterial route, so it was about 5 miles shorter if you took the arterial route. What Kyung-Oh did was each day he would leave at the same time and basically flip a coin and decide which route to take. We had 21 realizations of the highway route and 18 realizations of the arterial route. And then using that data, we actually had a GPS unit on his vehicle which recorded second by second speeds. From that we could compute the accelerations, and then from that we could compute the fuel consumption and emission levels for each trip using the VT micro model, which is shown here on this slide, which is a statistical model. It entails each vehicle has 32 parameters for a specific vehicle, 16 parameters when the vehicle is either accelerating or cruising, and another 16 parameters when the vehicle is decelerating. The model was developed using EPA data, and these are the description of the EPA data that we use to develop the models. So using the VT micromodel, in order not to bias our results, I guess, and remove the effect of a specific model, we actually ran it with a number of models. One of them was VT micro. One of them is the CMEM model, which is a model developed at UC Riverside. And both models seem to indicate that for this specific trip, you are better off using the arterial route, which was the shorter distance one, but the longer travel time route compared to using the highway route. The other thing that we found is that if you used the Mobile 6, which is a more macroscopic model, which was developed by EPA, it would give you the opposite conclusion. It would tell you that you are actually better off using the highway route if you're looking at AC emissions than using the arterial route. All the microscopic models, and those are VT Micro, MOVES, which is another EPA model, CMEM, all said the different conclusions. So based on these results, what we can conclude is that if you use a macroscopic approach, you can derive wrong conclusions because you do not capture the vehicle acceleration effects as they travel on a specific route. The other thing that we found in this study was that if you were to rank the highest fuel consumption and emission events in descending order, so for example, if you were to choose the highest 1% of those events, those would emit 16% of the total trip HC emissions, 19% of the CO emissions, 4% of NOx emissions, 3% of CO, consume 4% of the fuel consumption. And so you could then go down for maybe the top 2%, 5%, and 10%. And basically that is telling you that if we could clip off those aggressive driving events from the driver behavior, we could actually save some significant fuel and vehicle emissions. For example, the top 10%, if we could clip those off, we could save 25% of the total trip fuel consumption. So this ties into the eco-driving. So with that in mind, then we'll jump into what we're doing here as part of the MATS project. So we were looking, so in the previous study that we did, we actually looked at just a single vehicle and how that would affect, and how the route would affect its fuel consumption. The question becomes, what if we told now all the vehicles to use the fuel-efficient route? Could we make things worse by sending everyone on the arterial route, and then things would become worse for everyone? And so these are some of the publications. Initially, the publications were done as part of the TranLide UTC, which is headed by Idaho, but then later on, Ahmed, who's actually on the line, Ahmed al-Birri, he's a PhD student, he extended the work and looked at adding some communication facilities within the integration software, and also improving on the eco-routing system using some ant cloning based approach. Okay, so to just give you a brief background of the integration software, we have 10 different traffic assignment algorithms within the software. These vary from real-time algorithms to non-real-time, but I'll describe these in the next slide. The integration software tracks every vehicle every decisecond, so every 1/10 of a second. So initially we compute the route that you're going to be taking from your origin to your destination. We also identify which lane you should be in, and then once we identify which lane you should be in, we compute what speed you should be traveling at, depending on how close you are to the vehicle ahead of you. We have a steady-state car following model, which is the Van Aert model, plus non-steady-state conditions, which is a vehicle dynamics model to capture the vehicle accelerations, and a collision avoidance model to compute the vehicle speed based on the speed differential between you and the vehicle ahead of you, and the steady-state model. And this is what we call the Rakha Pasumati Ajreed car following model, the RPA model, that's embedded in the integration software. Given that the model computes the vehicle speed every decisecond, every second, we use the vehicle speed and accelerations to compute the vehicle fuel consumption and emissions using the VT micro model that we presented earlier in the presentation. In terms of the eco-routing logic that we have in the software, basically it's a feedback system that is based on vehicle connectivity. So we're assuming that vehicles have some connectivity to the TMC. That could be through some wireless communication, either a cellular or Wi-Fi. When a vehicle traverses a roadway segment or a link, it reports to the TMC how much fuel it consumed on that link. That information is fused with information gathered from other vehicles that send in their information. We do some smoothing of that data, and then the routing of future vehicles is based on the fused data that is an amalgamation of all the information that we receive from the different vehicles that can communicate with the TMC. Now this information is vehicle class specific. So for example, if you're an HOV vehicle that uses HOV lanes, your fuel consumption is going to be different than if you were not an HOV vehicle that would use the regular lanes. And so the fuel consumed for the HOV vehicles is stored in a different matrix than would be for the SOV vehicles. The same thing could be for trucks. The same thing could be for buses and so forth. Okay, so we tested this on two networks. Initially, one of them is the Cleveland network, which I'm illustrating here. This network entails a three-way that goes diagonally across the network with arterials on the network. And we also tested it on another network, which is more a grid-like network, where we had two east-west freeways and two north-south freeways. This is in Columbus, Ohio. Again, we wanted to see how the topography of the network could affect the potential results of these systems. And the next slide will just show you some specific information about these networks, but it will be sufficient to say that basically for the Cleveland network, we were modeling around 65,000 vehicles. This was the AM peak, 1 hour in the AM peak, and we had calibrated this network to loop detector counts using a synthetic OD estimator and using some planning ODs that we got from a planning model that they had for the network. The results for both networks show on the x-axis here we have the level of market penetration of vehicles that route themselves to minimize their fuel consumption, and on the y-axis is the average fuel consumption. But the key points here is that we observed reductions in the fuel consumption of the network somewhere between 3% and 9%, with increases in the travel time somewhere between 3 to 5% when we routed the vehicles to minimize their fuel consumption. As the level of market penetration of these equipped vehicles, of these eco-routing vehicles increased, the fuel consumption benefits increased, which was a good conclusion. And that these were observed for both the Columbus network and for the Cleveland network. We observed more benefits for the Columbus network, where we had more opportunities to route the vehicles because it was the topography of the network provided that for us. We also tested the results when we varied the level of congestion, so we increased and decreased the level of congestion. And the key finding that we found was that for higher levels of congestion, we typically seem to observe better benefits in terms of the eco-routing system, which is a good conclusion as well. We also tested the results for different vehicle types, whether they were fuel-efficient vehicles or non-fuel-efficient vehicles. And again, we found that the results were better when we were routing non-fuel-efficient vehicles. As part of the Match UTC, basically Ahmed, who's a PhD student here at Virginia Tech, extended the routing algorithm within the integration software by developing what we call an ant clone optimization technique. And basically, in a nutshell, what we did is we enhanced the model in two ways. One of them, as I mentioned before, that the information that we send to the TMC was only updated when a vehicle traversed the entire segment, the roadway segment. With the ant cloning technique, we allowed the algorithm to update the TMC even when the vehicle was still traveling along a roadway segment and had not reached the end of that segment. And we would project what would be the total fuel consumption on the entire segment based on how much it consumed on the portion that it traversed at that point in time, assuming that it would continue at the same rate if it would continue for the entire link. And so basically using the ant cloning techniques, we could actually update the information more frequently, and this becomes more critical when you have an accident, for example, on a roadway segment that basically blocks the traffic from traversing that roadway segment. In the old version of our routing algorithm, there would be no updates to the information, and so basically the vehicles would not be able to use what the other vehicles encountered up to that point in building their minimum path trees. And so with this enhancement, they could do that. And we found by comparing this enhancement to the model that we showed before, we could get savings somewhere between 2 to 6% that increased as the traffic demand increased on our network. Another thing that Ahmed did was he integrated the integration software with communication software. So in the integration software, we assume that if a vehicle wants to communicate with the TMC, there are no bottlenecks in the communication system, there are no loss of packets of the information between the vehicle and the TMC, and so we tried to get a realistic modeling by using the OpNet communication software and integrating that with integration software, and then capturing any losses of packets that would occur when you have a lot of packets being sent between the vehicle and the TMC, and any delays in the communication system that would occur when you have congestion in the communication network. That would delay the information that gets sent to the TMC, and so then the TMC would only be using data that will be either lost, that would be delayed, caused by the TMC, or if the data were lost, then it would not be using that data. Now, the algorithm that we have is based on a feedback system rather than a predictive system. So basically, you build a route from your origin to a destination, and then as you travel along that route, if traffic conditions change, we could reroute you at any decision point along that route. Another thing that we could do is predict what the traffic conditions would be into the future, and that is some of the work that Dr. Majid Seton at ODU is working on, is coming up with predictive algorithms, and these are some of the he's using probe data to predict what the future conditions of the network would be, and these are some of the results, the initial results that they have from ODU, but hopefully in the future we can discuss these results in more detail. So that ends the section on the eco-routing and gets into the next section, which is on the eco-cooperative adaptive cruise control systems, both on freeways and on arterials. We did, as previous work, do work on the freeways. However, I see that I'm running out of time here, so I'm just going to maybe not describe this one very much, but just to say that basically we use a dynamic programming algorithm that looks ahead on the roadway, so it looks at the topography of the roadway. So for example, if you're driving on a roadway that has a downhill followed by an uphill, then you might speed up on the downhill to get some momentum when you're negotiating the uphill system in order to minimize your fuel consumption. The driver of this system not only inputs a desired speed, but also inputs a minimum speed that they're willing to accept and a maximum speed. And using dynamic programming, we try to find the optimum trajectory of the vehicle to minimize its fuel consumption in such a way that it is as close as possible to the desired speed and within the range of the minimum to the maximum speed. And this is our objective function here, which is some function of the fuel consumption, some weighting that we want to be as close as possible to the reference speed, and basically we want to minimize the number of gear shifts that the vehicle has to do in order to attain that speed. We tested this on a trip from New York City all the way to Los Angeles, which is about 2,800 miles long in MATLAB. We assumed that there were no other vehicles on the roadway, and basically we tried to minimize its fuel consumption to get from New York to Los Angeles. We observed that we could get benefits in fuel consumption somewhere in the range of 10% if you're looking at a Toyota Camry, around 17% if you're looking at a Chevy Tahoe. But however, you're going to incur additional delay and reach to your destination 7% longer for the Camry versus about 8% longer for the Tahoe. So if you want to get there on time but still minimize your fuel consumption. You can get around 5% savings of fuel consumption, arrive there on time, and around 9% savings of fuel consumption for the Chevy Tahoe, and arrive there on time. Now, if you have other vehicles on the roadway, you need to also consider car following behavior, and we extended this to look at not only an adaptive cruise control system or a cruise control system, but we made it into an adaptive cruise control system where it would actually look at the vehicle ahead of it. Now I'll jump into the work that we're doing in terms of the Eco-Cooperative Adaptive Cruise Control System. Basically, the system that we're developing here assumes that you have some communication between the vehicle and the infrastructure. The infrastructure can tell you, can inform the vehicle of what we call SPAT, which is signal, phasing, and timing information. We're looking at a scenario where a vehicle is arriving at a traffic signal that is red and will be turning green sometime in the near future. And so if that controller could tell the vehicle that I'm going to be turning green in, say, 10 seconds, and if I knew that there were 3 vehicles in queue at the stop line, then I know I need to delay this vehicle by about 20 seconds. And the question that we're trying to answer is, how can we delay this vehicle in a fuel-efficient manner in order to minimize its fuel consumption? So we, in this slide here, we show you the trajectory of vehicles of drivers who are uninformed, and what we want to do is change those trajectories to be these red trajectories where the vehicle would slow down upstream in order to incur the same delay, but in a fuel-efficient way so that it arrives at the stop line just as the last vehicle in queue is departing from the queue. And in order to do that, what we have to do is predict when the queue is going to be discharged. So we came up with techniques to estimate when the queue will be discharging in order to compute the delay that we need to delay you by in order to have you travel through the intersection in a fuel-efficient manner through the intersection. So we, in this slide here, we just show you the normal driving. Then we show you the Eco-Cooperative Adaptive Cruise Control driving if we do not consider the queue. And then we could show you the same behavior if we were to consider the queue prediction that we developed. So in terms of the results that we found, we incorporated this in the integration software, and we tested it in 2 scenarios. One of them was a single lane approach, and on the x-axis here we show you the level of market penetration of these Eco-CACC equipped vehicles, and on the y-axis we see the savings in fuel consumption for the entire system. But what we can see is that as the level of market penetration of these equipped vehicles increases, the benefits of the system also increases, which is good. It seems to flatten out after you reach a level of market penetration of around 40%. The red line shows you if you were to predict the queues, without the queues, sorry, and then the green line shows you the benefits if you were to predict the queues. So you get better benefits if you were to incorporate the queue prediction in your model. Now, we also tested it on a 2-lane approach, so 2-lane in each direction. And so basically in this case here now, vehicles can overtake the vehicles that we are controlling. And what we found in the 2-lane approaches is that until you get a level of market penetration of around 25-26%, that actually by having the system running, you actually get disbenefits, around 5% disbenefits in the fuel consumption. And that happens because the other vehicles see the vehicle is trying to slow down and they don't understand why they're slowing down so early on. They are more aggressive drivers, and so they overtake and then cut in front of that vehicle. So overall, the system actually has higher fuel consumption levels, but then as the level of market penetration increases and the vehicles are forced to follow these Eco-CACC equipped vehicles, then you actually get benefits in your system. So with that, I'll conclude my presentation and open the floor to any questions that you might have. Maybe now we might have just a couple of questions, and then maybe we can open the floor after we have the second presentation. I'll let Emily, I guess, manage these questions as she sees fit.
Yep, no, I think that was great. Thank you, Hesham. And definitely, if people have questions and you can type them into the chat box, that would be great. I think everybody's audio may work, so you can probably ask it orally as well. I will go ahead and try to switch to our next presentation as people think about their questions. If nobody has one, then I wanted to ask about so what you, Hesham, what you did for the cruise control, that would be, if I get, some kind of cruise control in my car right now, would I be able to get benefits like that? Or how is it different? What's in my car right now?
Yes, so actually we do have another project that we got awarded in the competitive one where we would actually be having it in the field. So basically, you would implement the system on top of an adaptive cruise control system where you would have some form of communication, DSRC or Wi-Fi or cellular, between the intersection controller and the vehicle. And then what we would do is we would update the recommended speed for the ACC system in real time rather than having the driver input that speed that they input into the system.
Okay, so it's using the current equipment, but it's using the communication with the infrastructure.
That's correct. Plus some additional logic on the current instrumentation.
Right. Okay, I got it. So I don't see any other questions. I think we will have time for questions at the end of this, so please think about your questions. We can definitely type things into the chat box and keep going here. I mean, if you guys are working on research related to these things, I'm guessing you may have questions as we hear both sets of presentations. So I want to now introduce Yongqiang and Wang. And I think we may start the presentation with his advisor, who is Ajay Prasad at University of Delaware. So if you guys want to go ahead and start your presentation.
Okay, we'll get started. Good afternoon, everybody, and welcome to this second webinar hosted by the University of Delaware. The title of our work is Connected Vehicle Technologies for Energy Efficient Urban Transportation. Our focus here is going to be on hybrid vehicles. In particular, we are going to be talking about fuel cell hybrid vehicles. This work has been done by my PhD student, Wang, and my name is Ajay Prasad. I'm a professor of mechanical engineering at the University of Delaware. I'm also the director of our Center for Fuel Cell Research. And John is co-advised by Suresh Advani and myself, and he's supported on a grant from Mass UTC. Okay, so the outline of our presentation today is first I will talk about our fuel cell bus program at the University of Delaware, just provide some historical perspective. And then I want to spend a few minutes for those who don't know what exactly a fuel cell is and how it might be superior to a diesel or a gasoline-powered vehicle. I will also spend a little bit of time going into the drivetrain of a hybrid fuel cell battery hybrid vehicle, because it's important to understand that aspect of it before John comes along and takes the next two bullet points. So then after I'm done, John will jump in and he'll talk about connected vehicle technologies in general, and specifically he's going to talk about V2I, vehicle to infrastructure. And what we mean here is that vehicles in the future are all going to be communicating in real time with the TNC. And so there will be some central server which will be accumulating data from all vehicles and the TMC will be able to identify regions of traffic congestion. Perhaps there's been a traffic incident on the road. This information is actually very, very useful, as John will show. Essentially, every vehicle then becomes a traffic sensor in itself because it is communicating its location and its real-time velocity to the TMC. And so that leads us into the third bullet point, which is how do we use this real-time traffic information to predict the workload of a hybrid vehicle. And more than that, how can we use that workload prediction to intelligently manage the power on board these vehicles? And in particular reference to fuel cell hybrid vehicles, we will show that we can use this data to maximize fuel economy. And an added benefit is that we can also use this information to maximize the system life, because as John will talk about this, fuel cell vehicles do not like to be turned on and off frequently. So we can actually use this upcoming traffic information to give us some guidance about that. Okay, so a quick introduction to our fuel cell bus program at the University of Delaware. It's an ongoing program commenced in 2005. We currently have 3 fuel cell buses on our campus, which we use to transport students from their dorms to the classrooms. Bus 1 was introduced into our fleet in 2007, Bus 2 in 2009, and Bus 3 in late last year, 2015. The bottom right there shows our refueling station. This was built by Air Liquide, just about 5 miles away from campus. It's maintained by Air Liquide, so that's where our buses go to refuel as and when required. The hydrogen fuel cell, the fuel tanks are in the roof of the bus. You can see the hump at the top of on top of the roof. That's where the hydrogen tanks are located. And the entire fuel cell system, if you open the back panel, back doors, you can actually see the entire system right in front of you there. I don't have a picture of it, unfortunately. Importantly, all of these vehicles are fully equipped with all kinds of sensors, as well as a GPS tracking unit. And in real time, this information is collected by a server in our lab using a cellular link. And so we have many years of data that we have archived, and we are now using that historical data to test some of our optimization algorithms. Okay, so what exactly is a fuel cell? So the picture, the schematic on the right, tells you how a fuel cell works. So the fuel in this case is hydrogen. We use very high purity hydrogen as the fuel to the system. So the fuel comes in at the top left, and it undergoes an electrochemical reaction, and the excess fuel exits at the bottom left. The electrochemical reaction is between hydrogen and oxygen. The oxygen is extracted from the air, so we supply air with an air compressor to the fuel cell stack at the top right of that picture, and as it flows, the oxygen is extracted and the excess air flows out through the bottom right. The beauty of this entire process is there is no combustion going on here. This is not an internal combustion engine. This is not a heat engine. Therefore, the efficiency is not limited by typical Carnot cycle efficiency considerations. This is an electrochemical reaction where the chemical energy contained in the hydrogen fuel is directly converted to electrical energy, and we can use that current and that voltage to drive the traction motor on our bus. So what is the product of the reaction between hydrogen and oxygen? It's just plain old water, and what comes out of the tailpipe of the fuel cell vehicle is just water vapor. On a cold morning, you might see water droplets, but there is no carbon dioxide, no carbon monoxide, no NOx, no SOx, no soot, nothing. So on the left there, I have a couple of bullet points about the benefits of fuel cell vehicles. Because it's not a heat engine, you get very high efficiencies, about 2 to 3 times the efficiency of a conventional gasoline or diesel powered vehicle. Also, these vehicles are zero emission because all that's coming out the tailpipe is water. And if you produce that hydrogen from a non-fossil fuel source, that's a good thing because that helps to reduce our nation's dependence on foreign petroleum. Okay, so one more slide from me, and then I'll hand it off to John. Let me tell you about what the typical drivetrain looks like for fuel cell battery hybrid vehicles. So if you look at the schematic drawing on the right there, at the top you have the hydrogen tank. The hydrogen flows through a regulator. It enters the fuel cell. It undergoes the reaction. The fuel cell produces a voltage and a current. Typically, the voltage is not sufficiently high, so we pass it through a boost converter to jump it to 300 volts or 600 volts, depending on what your system is configured for. The voltage coming out of the fuel cell is DC, whereas our traction motor is an AC induction motor, so we have to pass it through an inverter to convert DC to AC, and that's how we drive the traction motor, and that's what drives the wheels. You'll notice there is a battery that is attached in parallel to the electric drivetrain, and what we have in our bus is a battery-dominant hybrid configuration, which means to say that the fuel cell's job is to work so as to keep the battery topped up, depending on certain rules that we employ, and it's the battery's job to actually drive the vehicles. So the fuel cell and the battery work in a combined manner to drive the vehicle. And of course, the advantage of any hybrid vehicle is that we can take advantage of regenerative braking. So when the driver applies the brakes, the kinetic energy of the vehicle is converted through that same old traction motor, which now acts like a generator, and it converts it to electrical energy, which is stored in the battery for future use. So to summarize the benefits of this drivetrain, first of all, we have all the benefits of a fuel cell vehicle because we have high efficiency, we have zero emissions, all of that good stuff. We have all the benefits of an electric vehicle because this is a purely electric drivetrain. It has no noise. And as you know, the round-trip efficiency of a battery is very, very high. But where these fuel cell hybrid vehicles depart from an electric vehicle is that our driving range is very similar to a gasoline or a diesel. So we don't have any of the typical range anxiety problems that pure electric vehicles have. And most importantly, we can refuel hydrogen into our bus in about 10 minutes, which is very comparable to a diesel vehicle. And it is unlike the hours that you might need to recharge an electric vehicle. So with that, I'm going to hand it over to John, and he's going to talk to you about what he's been doing in terms of his results.
Okay. Hello, everyone. This is John from University of Delaware. So with all those connected vehicle technology available, we have all the communication system to get traffic emission information regarding congestion incident for the vehicle. So from our perspective, from the vehicle perspective, we want to use those information to improve fuel economy. And also, as we showed before, from the traffic management perspective, with those connected vehicle technologies, we can send data to the server, to the TMC. So as I show here, this is the recorded velocity profile for bus 2 on a certain segment of the bus route. So those data are from the previous 3 years. So as you can see here, most of the time the velocity profile is pretty consistent, but sometimes the bus will stop in the middle of the segment, which means you have a longer queuing on that segment. So that means with our bus as a traffic sensor, we can extract all the usual information regarding traffic, such as average velocity and length of traffic queuing on the route. So those information are very useful from a traffic management perspective. And then after we get all those traffic information from the TMC, how do we use those information? So for the power management on the vehicle, traditionally you only have say gasoline or diesel engine. You only have one power source, and normally the fuel consumption is directly proportional to your power demand to see how much you accelerate or your cruising velocity on the highway. But on our hybrid vehicle, normally it's much more complicated. So normally you have two or more onboard power sources. In our case, we have fuel cell stack and we have battery stack, battery pack. So to improve the system efficiency, normally it's not just proportional to the power demand. It also depends on your state of power sources, such as battery state of charge or the power level from the fuel cell stack, because each different power source has different efficiency curve. So the prediction of the future workload is very useful when we are trying to maximize the fuel efficiency of the whole system. And also later I'll talk about the system life for the fuel cell stack specifically. So with all those parts working together, we have the framework of the control system basically. On the right, we have the detailed physical vehicle model. For our bus, we have fuel cell, we have battery to drive the motor. And then on the bottom left, we have all the information we can possibly get from the TMC, such as traffic information, geographic information, such as road elevation. So those information can easily be converted to the velocity profile, including delays, including slope of the road. And then they can be fed into our optimization algorithm, which will convert those velocity profile to workload. And then normally for different vehicles, you have different optimization objectives. So traditionally for gasoline engine vehicle, normally you only consider fuel consumption and emission. But for the fuel cell stack, we don't have emission, so that's good. But we do consider fuel consumption. And in addition to that, we also have to consider durability of the fuel cell stack. Because as Dr. Prasad just said, fuel cell stack does not lack frequent off cycles. It will put a lot of stress on the fuel cell and decrease the lifespan of the fuel cell stack. So we also add durability to the cost function as another objective. So the optimization algorithm will then give you the optimal control commands based on your prediction of future workload to the vehicle. So the vehicle can operate at the optimal in an optimal way to improve the system efficiency.
Yeah, if I can just jump in with a quick example here. If you think about a vehicle that knows that in the next 30 seconds it's going to experience a hard braking event, then the traffic, the onboard power management controller can, on purpose, make sure that the battery state of charge is depleted because it knows that it has to expect a surge in regen current. So that's one way to think about it. Or if the controller knows that in the next 1 minute it's going to experience a sustained climbing event where a lot of power is required, then it can make sure that the battery state of charge is topped up prior to the event.
Okay. So here is one of our main results. So the graph shows here on the top you can see the optimal battery state of charge trajectory. And then in the middle you have fuel cell stack power. And then on the bottom you have fuel consumption, accumulative fuel consumption. So the blue line here corresponds to the traditional rule-based controller, which basically the system will turn the fuel cell stack on when your battery SOC drops to a certain level. So in the middle, you can see for the rule-based controller, the blue line here, it's trying to maintain when it will turn the fuel cell stack on later in the drive cycle, and then it will turn on off very frequently, relatively frequently, to maintain the lower SOC limit. And then the orange line shows you the result from optimization. So in the middle, you can see if the system knows the future load, in this case for a 2-hour drive cycle, it will try to turn the fuel cell on beforehand and operate at a relatively optimal efficiency region, so that the overall fuel consumption for the whole drive cycle will be smaller than the rule-based control strategy. So on the bottom left, I show you the fuel consumption for this specific drive cycle. So if you don't use the optimization, you only use the rule-based charge sustaining control strategy, you will consume 1.39 kilograms for this drive cycle of hydrogen. And then if you do the optimization, it will only consume 1.19 kilograms of hydrogen. So that's approximately 14% fuel reduction. So we also mentioned the fuel cell durability in the previous slide. So right now the cost is still a major barrier for the commercialization of fuel cell vehicles. Although all the automakers are trying to release their fuel cell vehicle, it's still relatively expensive. So we want to add durability as an optimization objective to our algorithm, because as you can see here, this is the same drive cycle from previous slide. On the bottom, for the rule-based controller, the blue line here, you turn the fuel cell stack on or off very frequently. So during off cycles, it will put a lot of chemical and mechanical stress to the fuel cell stack. Chemical stress is due to the high startup chemical potential when you turn on the fuel cell. Mechanical stress because the memory inside the fuel cell basically will swell when it's working. It will shrink when it's drying, when it's not working, basically. So that puts a lot of chemical and mechanical stress. So we want to add the off cycles as a penalty to the cost function. And as you can see here, the orange line shows you the optimization result, which basically the fuel cell stack will turn on early, and then it doesn't have to turn off during the whole drive cycle. So that's very, very good for the durability. So the ongoing research is focused on the real-time controller. So we also use the optimization algorithm, as Dr. Hesham just said. We also use the dynamic programming algorithm. So as we know, it will be relatively slow now that you have to consider the state of the power source. So I think for traditional gasoline engine, your state space will only be velocity and gear ratio, maybe. So your state space is relatively small. But for hybrid vehicle, now you have fuel cell power as your control space. And then for the state space, you have battery SOC, you have velocity, you have everything. So the control space, the control state space will be much larger. So it's relatively slow. So how do we implement it in real time if we can get a real-time traffic information? So the current research focuses on to build a neural network learner. So basically, we can get the optimal control strategy from previous dynamic programming algorithms. We fed those optimal trajectories, optimal control strategies to the learner. So the learner will be based on the current SOC state of charge, based on future workload. It will give you the optimal control strategy for the vehicle, and it can be implemented in the real time after you trained the learner. So, and then our bus 3, which is which was just delivered late last year. The power management system on the bus 3 is capable of being controlled remotely. So right now it's communicating with our server through the campus Wi-Fi, and the server can then send the upcoming traffic information to the vehicle. Then the vehicle will use those information to predict the workload, and then use the real-time controller to optimize fuel efficiency as well as the system durability. I think that concludes our presentation. Thank you, everyone.
Great, thank you. That was great timing too. Do you guys have any questions? You know, if you do, please type them in. I know before somebody raised their hand, and I've asked them to type in a question, and I'm not sure he still has that question. So I think I do have, you know, one question for Delaware, and then I think we can open it up to questions for either presenters or either of the presentations. So my question, John and Ajay, is, you know, so you're interpreting connected vehicles as the fuel cells, or the fuel cell vehicles, you know, talking with the infrastructure for better energy management. Is that what I'm learning? I mean, if you didn't have the energy management problems and the communication problems, you know, I guess what would be the ideal use of the fuel cell vehicles in a connected vehicle environment? Does that make some sense?
Right, right. Yeah, let me see if I understand your question, and then one can also jump in and add something to that.
Okay.
Yeah, so we are primarily, we want to use information from a central server in order to be able to predict the workload. So the information is primarily used to help us predict the future workload, which will help us draw power intelligently from various onboard sources, in this case the fuel cell or the battery, and in a manner that will help to reduce our fuel consumption, and as well as improve the life of our onboard systems. So I think the second part of your question was, what if you didn't have this information? What would we do? Well, what we would do is use like the previous, let's say, average, let's say a half-hour or 1 hour average, and basically, you know, keep changing our power management strategy based on the historical on the recent past history of the drive cycle. John, did I say that right?
Yeah, so also, since we collect historical data for the previous drive runs, so we can also use those information to give a prediction of the velocity profile in case there is no real-time traffic information. So the optimization is still valid for those cases, just how the difference here is just how you get the traffic information. Either real time or from modeling the historical data.
Right. Okay. Thank you. So I think I've seen somebody starting to type a question in. So again, please share questions. Here we go. So from Guoyan Wu, what model of fuel cell bus are you using in your optimization or simulation?
Oh, we actually have an extra model for our bus. We are not using the generalized like vehicle simulator like Advisor. We are not using that. We have a specific model for our fuel cell bus, and we did have students collecting all the data, or the efficiency model, or the fuel cell stack efficiency model, or the battery pack. So we have all the experimental data from the bus, and we actually build a kind of simulation model based on the physical model of our bus. So yeah, I hope that answer your questions.
So I think he's typing in. So, but you're so it's a Delaware built model. It's not some off-the-shelf commercial model.
Correct. Yeah.
Okay.
This is Hesham. I actually have a question for the folks at Delaware. I guess I've been doing, I guess my PhD was on traffic signal control, and one of the biggest issues that we had was if you, I guess, regardless of how good your optimization is, if your prediction is wrong, you've got a wrong solution. Is that correct? So that your entire methodology hinges on your ability to predict the future. And what we found in traffic signal control is that because traffic is so stochastic, in the majority of cases, your prediction is going to be wrong. And so basically what it comes out to be is in your control algorithm, you're trying to minimize coming up with outrageously wrong solutions, I guess. So basically you want to minimize the error that you're going to make. And so basically you constrain your optimization so you can only make small changes so that if you make a mistake, it's a small mistake and not a big mistake. If you could reflect on that and your thoughts on that in terms of your algorithm and so forth.
Yeah, so we actually now using the optimization algorithm to do a sizing study of the bus. So for that perspective, it doesn't really matter so much because we're only considering the average fuel consumption. But yeah, to answer your question, so in the real time, normally what we do is we do an MPC controller, so model prediction controller. So what it does is it predicts, say, for next half hour, the workload of next half hour, and then you get an optimal control strategy. And then you only implement this control strategy for, say, first 5 minutes. And then you get, after 5 minutes, you get a new information, and you run a new optimization, and then you implement it for another 5 minutes. So that's how you normally implement in real time for the controller. Yeah, but you are correct. If your prediction is wrong, your optimization will be wrong. But in real time, you will keep kind of updating your optimal control strategy and then keep implementing them for only a short time. Yeah.
Yeah, I mean that's what we do. It's a moving horizon. We move with the vehicle, but predicting the topography of a road is much easier than predicting traffic. Traffic is very stochastic. I mean, you have one advantage, it's a bus. And so buses are typically stopping at bus stops and so forth. But if this was implemented in a car, I can tell you your prediction is going to be very, very bad.
Okay.
Okay, so we have another question in the chat box about, are you requiring initial SOC and final one to be the same? I'm not.
Yeah, so it depends on how you implement, what's your purpose. I mean, if you, as I said, if you want to do a sizing study, the initial and final SOC doesn't really matter. But if you want to implement it in real time, you want to say whether you want to drain the battery at the end, or for a bus, normally the bus will run for 7 or 8 hours per day, and then you only optimize, you only run the optimization for the first 2 hours. So in that case, your initial SOC and the final SOC normally will be the same, so that you can continue kind of run the bus throughout the day. So yeah, it depends.
Another way to think about it is your answer will depend on a couple of things. It will depend on, first of all, what is the size of your battery pack. Secondly, it will depend upon what is the cost of electricity for recharging your battery. Third, it will depend upon what is the cost of hydrogen. So if your electricity cost is very small compared to the hydrogen cost, which is what is true today, then it actually makes sense to deplete your battery state of charge to as low as possible before you pull into the depot, because then you can plug your bus into the socket, into the charger, and then you can recharge your batteries using grid electricity, because that would be a cheaper way to do it. So these are strategies that can be implemented within the cost function.
Okay, so then we have another question. How do you consider the bus stop in your trajectory power prediction?
So from historical data, we know where the bus stop is obviously. So it won't be a major problem for the optimization algorithm actually. So as long as you fit in the velocity profile, it doesn't really. I don't think the bus stop specifically matters for the optimization. Yeah.
Okay, so we got to thank you very much. So back to our, what AJ was saying about, draining the batteries, or draining the electric battery at the end of the day. So typically, do the Delaware buses, fuel up, with hydrogen a couple times a day or a couple times a week? I mean, what's the typical use of these buses? You said that they're used for 7 to 8 hours a day. What percentage of that is electric and what percentage is hydrogen?
Okay, so for buses 1 and 2, the typical range on pure battery alone is about 15 to 20 miles. So actually 7 to 8 hours, we don't typically do that. We have done that on special occasions, but typically our routes are more like maybe 2 to 3 hours. We want to kind of use these buses middle of the day on high visibility routes. Part of our mission is to get to do a lot of outreach and public exposure to these buses. So we don't want to drive them early in the morning or late at night when nobody's around to see these buses. So the point is we kind of select the peak hours of the day, the best hours of the day to drive them. And so if you have let's say a 2-hour outing, so the first 45 minutes would be pretty much on battery power because you start at fully charged, and so then the remainder would be on hydrogen, and then when you come back to the garage, you plug it in, and then you do the same thing the next day.
Okay, thank you. That's helpful. So I don't think we have any more questions. I really appreciate both Hesham and John and AJ all talking with us today. We are going to put an archive of this on the website. If you want the presentations now, you can download them. We're also going to have them on our Match UTC site. And I hope that everybody attends future webinars. So, thank you very much to all our speakers. I think we can virtually sit here and clap for our speakers. Thank you, but I think everybody should have a good day. So thank you.
Thank you, Emily. Thank you for arranging this. Bye.
Thank you. Goodbye.
Thank you. Bye.